Good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Hey.
Okay, so let's get started on today's lecture. We will study this question. So this question is for this combustion reaction. So give you the delta H, and the first question is without using the data from appendix C, going to predicting the delta G for this reaction is more or less negative than the delta H. So let's do the first question first. We were using this equation to answer those questions. So this equation tells us delta H equals delta G equals delta H minus T delta S0. So to compare this delta G with delta H, so you pretty much just think about what this term will do. So this term has the T delta S. We know T is always positive. In this example, it's 298, and 298K is positive. So therefore, whether this term will make a positive contribution to this delta H or negative depend on this delta S. So for this question, and we can analyze how much gas we have for the reactant, how much gas for the product. We can get some idea about the sign of delta S. Okay, so let's take a closer look at this chemical reaction. So we have two reactants. Both of them are gas. We have two products. One is gas, the other one is liquid. So we can see there are 6 molecules or 6 moles of gas reactant, but there's only 3 moles of gas product. So therefore, the number of gas molecule has decreases, and we predicting delta S negative. So once we know this delta S is negative, So we can say we were subtracting a negative number. So we think about in this equation, delta G equals delta H minus T times delta S, because delta S is negative. So therefore, these two together is negative. T never negative. So T
Honestly, he teaches, but our PowerPoint's like
you cannot
be
see.
easier if you put points without him saying anything.
Questions?
You're trying to figure out what he's saying?
Yeah. No, I'm not really even paying attention to what he's trying to actually teach.
Okay, so
But
you can
he's
see
really
in this.
nice.
So delta G equals delta H minus T times delta S.
The Asian.
So therefore, delta G equals delta H minus a negative number. Okay. So as you know, minus a negative number, which means or subtracting a negative number means plus a positive number. Okay. So therefore, now it's clear. So you compare delta G with delta H. So you take delta H, whatever number delta H has, then you plus a positive number. So therefore, that will become more positive or less negative. So that's how we predicting or compare the delta H with delta G. So the second part of the question is using those given numbers, we calculate. So we calculate what will be the delta G. So what we use using this delta G0F. So this is one way to calculate delta G for the reaction. So the other way is using delta H and also delta S. So this way using delta G0F relatively easy. So just using this formula, I will give you those data. So this number, so-called the standard numbers from the table. So then you know this N and M are the coefficient. So we have this product CO2. We have this H2 liquid, these two products. Their coefficient for CO2 is 3, for water liquid is 4. So therefore, we just take those numbers. We have 3 times. So this 3 times whatever the number for CO2, and then 4 times whatever number for H2 liquid. So right now you see this is only 3 and 4, but actually when you take the coefficient from an equation, you know those coefficient has some meaning. So you can either use this as moles, 3 moles, or 4 moles. So sometimes you will see 3 molecular or 4 molecular. So we will here use moles. So therefore, this line you can see I'm using this moles. So this where this mole come from our convention. So we know when we have a coefficient, we will have the unit moles. So therefore, these moles cancel out with the moles in this given quantity. So therefore, we only have a kilojoule. So we do the same for the reactant. All right, so multiply and add, we get this negative number. You can see after we calculate, we have negative 2100. So this is delta G. So this is delta G0. You compare delta G0 with delta H, so that becomes less negative. So that's agree with our predictions. Okay, so next we want to study how does delta G change with temperature. So we pretty much going to use this equation. So this is another way to calculate delta G. Or you can use this equation. You can predicting how the delta G change as a function of temperature by assuming delta H, delta S do not change with temperature too much. Okay. That's very important because for a spontaneous reaction, we need delta G less than 0. So therefore, the sign of entropy, which means this delta H, and the sign of entropy, which means delta S, and the magnitude of temperature matters to the spontaneity. All right, so the next question is we have this Haber process to make ammonia, and we are given this delta H, delta S. We are assuming delta H, delta S do not change with temperature. So therefore, we first want to predict the direction in which delta G for the reaction change with increase in temperature. Then we'll calculate this delta G at two temperatures, 25 and 500 degrees Celsius. So to predicting how this delta G change with temperature, we just look at this delta S. We will see what is the sign of this delta S. Then we are using this equation. Okay. So in this problem, delta S, so here this delta S is a negative number. So negative number, that means you minus a negative number or you subtract a negative number, which means you plus a positive number. So on the next slide, we'll see if you plus a positive number, then how big, how small is the positive number you add on? Obviously depend on delta S, but also depend on the temperature. So therefore, as the temperature become higher and higher, so therefore, if this you adding, we consider this, you are actually adding a positive number. So therefore, the result for the delta G become less negative with increasing temperature. So delta G is we can think about delta G is a driving force for the reaction. So when the delta G is negative, more negative means more driving force. More driving force, which means it favors more of the product. So we're predicting for this ammonia synthesis reaction as the temperature increases, so it favors less of the product. So then we next want to confirm our prediction. So we're still assuming delta H, delta S do not change with temperature. Now we are going to calculate this delta G at two temperature, 125 degrees Celsius. So you need to convert it from Celsius to Kelvin. So therefore, we will use 298 Kelvin and using the given delta H. So this is the delta H. Then this is our temperature. Then this will be our delta S. What this guy do is convert. You want to convert from J to kJ. Because you cannot add in two numbers have different units. So if we keep delta H is kJ, we need to convert this J from delta S into kJ. So we calculate, we get delta G equals negative 33.3 kilojoule at 25 degrees Celsius. We'll do the same for the other temperature. Okay, we're assuming delta H, delta S still the same number. So therefore, we still keep this delta H, we're still using this delta S, the same idea. So here is a conversion. So here we want to convert from J to kJ. And you get 61, positive 61 kilojoule at 500. So therefore become more positive or less negative. And that is agree with our prediction. Right, so the practice question for this Haber process is predict at what temperature above, at what temperature that hardware process become non-spontaneous. And from last slide, we can see there are two delta G. So we have a delta G negative at a lower temperature. So this is 25 degrees Celsius. And this is 500 degrees Celsius. So clearly we can see the transition of a delta G from a negative number to a positive number. So then this question is, at what temperature precisely you will have a positive delta G? So when the delta G becomes positive, that means our reaction becomes non-spontaneous. So to do that, we just using the number, assuming this delta H, delta S do not change with temperature, then we use our equation. So delta G equal to this. And we know when delta G less than 0, spontaneous. When delta G larger than 0, non-spontaneous. So when delta G equal to 0 is the transition point or equilibrium. So what you do is just setting this equation to 0, and you have the number for delta H, you have the number for delta S, then make them have the same unit, then you can solve for temperature.
Dr. Wayne?
Yeah.
So does the equation become non-spontaneous when delta G equals 0, or is it the first time delta G equals a positive number?
Good point. So for any chemical reactions, when delta G becomes 0, become equilibrium. So to find out the temperature above, we're using 0. You are right. So for the reaction to become non-spontaneous, we need a larger than 0. So we can either using an inequality. So we can do that either. We can do that also. So therefore, let's do that. So we want to use delta G 0 larger than 0. So solving this one, you will get a temperature higher than something.
Thank you.
You're welcome. So let's take Steve. So let's take this delta H, and we write, we want this delta G larger than 0. Therefore, we want to write delta H 0 minus T times delta S 0 larger than 0. Then we just substitute and make sure this delta H, delta S have the same unit. So what you have is negative 92.38 kJ. Then minus temperature we don't know. So we have this. So we have this number here for delta S, which is negative 198.3 J per K. So therefore, as what we did for the first part of the question, we want to convert this into kJ, and we need this larger than 0. All right, so we still write this negative 92.38 kJ, and then we will write this become positive T times 0.1983 kJ over K larger than 0. Okay, so we turn the page and we will write negative 92.38 kJ plus T times 0.1983 kJ per Kelvin larger than 0. So plus 92.38 kJ. So we still write plus here 92.38 kJ. So these two cancel out. So therefore we have T times 0.1983 kJ over K larger than 92.38 kJ. So we divide 0.1983 kJ and divide 0.1983 kJ. And we also times K, which is unit, times K, which is unit, Kelvin. So we get T larger than 92.38 kJ divided by 0.1983 kJ times Kelvin. So kJ comes out, so therefore get T larger than 465.9 Kelvin. Convert this into Celsius, that becomes 193 Celsius. Okay, so you look back into the multiple choice, so the answer is D. Okay, so next, what study the free energy and equilibrium. So at any condition, the standard or non-standard, the free energy change can be found in this equation, which means delta G equals delta 0, which is standard, plus RT, L, and Q. You know what is Q? Q is the reaction quotient, and R is the gas law constant, temperature should be in Kelvin. So Q is the reaction quotient, and at a standard condition, which means all the concentration should be 1 molar, and if you have pressure should be 1 atm, so everything is 1. So therefore Q equal to 1, and if Q equal to 1, LQ is 0. So therefore you have delta G equal to, you will get delta G 0 equals delta G 0, which means this equation is true for any conditions. So what we want to use is using that equation to calculate some of those chemical reaction delta G that is not standard conditions. So this example, we still have the temperature is okay, kind of standard, but our pressure, this is standard, and this is not. This is not. So you want to calculate the delta G at non-standard condition, just using this equation. So delta G, a non-standard condition, then this is standard, and then this is the reaction quotient. Probably just review how you write the expression for the reaction quotient. So the reaction quotient, we give that a name Q, but the expression is the same as the equilibrium constant, which means you take the pressure or concentration of the product on the numerator, then the reactant in the denominator, then you take those coefficients as exponent. So therefore, for this particular chemical reaction, if we use the partial pressure, so the Q can be written as the partial pressure of our product NO3, and then this square come from the coefficient. So therefore, we have our typical way of writing the equilibrium constant, and we can also use for the reaction quotient Q. So once we get this expression, we substitute those numbers, and we calculate, we have this Q number. Next, you just plug this Q into this equation here, and calculate what is your delta G. So obviously, we also need to know what is our delta G 0, or what is our delta G not. So from one question.
Can you go back really quick, please?
Okay, so.
Thank you.
Welcome.
Okay.
Okay. So we from one question, we know our delta G naught is this number. So then we know we use R is 8.314 temperature in Kelvin. So we have everything, and we just yeah. So just a couple of points, and one point is this fraction here. So this fraction here, this fraction means 1 over 1,000. Why we have this fraction here? Because we need to convert. So this fraction is actually doing the conversion. So to convert from J to Kj. So therefore, you can add. So you can see this delta G not have Kj. So this R has J. So therefore, we have used this fraction to convert the first term here have Kj, second term also Kj. The second point is where this guy come from. Where this come from when you write the reaction quotient. So let me go back to the last slide. Okay. So when you write the reaction quotient, you can see those number here powers. So those powers are from coefficient. Remember, the coefficient have unit moles. So that's where this mole come from. So this mole come from the exponent of L and Q. Okay, so once we know what this guy do, where this come from, and then we use this number and multiply or take the logarithm, we get this number. Well, so this is non-standard. And this is standard. Okay? So for this particular question, we can see our delta G become more negative for this non-standard condition. Negative 44 compared with negative 33 become more negative. Okay. So that means if delta G is more negative, so our reaction favors more product. Is that agree with Le Chatelet principle? So Le Chatelet principle tell you where it shifts. It's shifting to the reactant or shifting to the product. So if we can also use Le Chatelet principle of predicting this new condition with compare with the standard condition, and then we can say that it agree. So at the standard condition, we have N2 and H2. We produce NH3. So 1 ATM, 1 ATM, and 1 ATM. So the non-standard condition, no, we still have this in 1, but this becomes 3, so this becomes 0.5. So if you think about it, you keep this still the same 1 ATM, you increase the reactant, so they are making the reaction shifting to the product. And this, what this do is you decrease the product, so that's also shifting the equilibrium to the product. So both of this change, according to the Le Chatelet principle, for shifting our equilibrium to the right, that agree with our number. So our number will get more negative. All right. So now, in particular, I think as one student asked the question, I think that is Steve. So when you delta G equals 0, so that's become equilibrium. So delta G or delta G 0 becomes 0. So either way, whenever this delta G becomes 0, so we have equilibrium. So at equilibrium, that means the reaction quotient Q equal to K. So therefore, we can, using this equation, and to calculate what will be our K. So we'll change this equation here, become 0, and then this becomes K. Then we get this new equation. So you rearrange this new equation, so you get this. So that means delta G naught equals negative RT L and K. So on the next slide, we are going to use this equation to calculate what is our K. Okay, so for this question, we are calculated, or if I give you delta G is negative 33,300, and you want to calculate what is the equilibrium constant at this temperature, 25 degrees Celsius. So using this equation, okay, and remember the R number, and also make sure if R is 8.314 joule and this is kilojoule, so you can either I write here joule, probably easy, but what you do, you are right. Well, here I write use kilojoules. All right. So therefore, we have this equation, and I think we should not have this promos. So therefore, we don't have promo here. So after that, we see where this come from, where this come from. The same idea as I explained for the a few slides before. So this is for conversion. This comes from the exponent. So therefore, we will see the mole comes out, and this is the Kelvin comes out, and then this J comes out, and this Kj comes out. You should have no unit. So therefore, you get this number 33.3, negative 33.3, then negative 2.478, and then Ln. I emphasize this KEQ to not confuse with this K. So this K is Kelvin. So obviously you take this negative 33.3 divided by negative 2.478 to get 13.44. Then next you take the exponential function. So KEQ equals e to the power 13.44. So you get 6.87 times 10 to the 45. So that's how you solving some of those questions. If I give you delta G, so better using this this way to understand. So where the unit comes out. I think probably the textbook will give you a little bit different approach, but I prefer this. So let's do a proof question. And last time somehow I did not get your answer, even though I practiced a few times. So today we'll do both way. So use your cell phone text, and then later on we're also going to use the proof function from Zoom. Okay, so let me open the pool. You can also click on the pool. Okay, well, you give some idea. If you see this chemical reaction equation, just predicting what will happen to the delta S. So for this chemical reaction, the delta S should be a positive number because you have 6 gas compared with the 3 gas. So the rule is if you write down, if your delta S is positive, then your delta G will be less positive than the delta H. So if delta S for the chemical reaction is positive, then your delta G is less positive than delta H. Okay, so this is just a practice. So I will try to check in both ways, checking my pool everywhere and also checking on my Zoom result. And I give everyone 1 point for Tuesday's pooling, even though I did not get the result. So today I will check the result. If you get it right, you will get 1 point. Okay, so I'll finish the pooling now, and we'll go to the next chapter. Okay, so we're going to start on the chapter 20, electrochemistry. Okay, so electrochemistry is the study of the relationship between electricity and chemical reactions, including the study of both spontaneous and non-spontaneous process. So in this electrochemistry, most of the time you will see those oxidation reduction reaction. So for short, we write redox. So we combine this part from the reduction with this OX to get one word, redox, to emphasize these two reactions. So sometimes we call them two half reaction. So half reaction is reduction, the other half reaction is oxidation. They always happen together. So then some of those fundamental definition is kind of review what you learn in Chem 113. When atom lost electron, it is oxidized. When atom gain electron, it is reduced. So that is the thing about lost electron or gain electron. More general is using the oxidation number, which we studied in chapter 5, chapter 4 of Chem 113. If we know the oxidation number for atom before the reaction, after the reaction, if the atom's oxidation number increases, it is oxidized. When atom's oxidation number decreases, it is reduced. So oxidation number is a hypothetical charge an element will have if electron were fully transferred to the more electronegative element. Oxidation number of atoms can be found following rules on the next slide. We studied those rules in Chem 113. So therefore, I will just go very quickly on these rules. Those rule has a priority. You will use the higher priority rule first to solve the problem if you can. If you cannot, then go to the next rule. So the first rule has the highest priority, which tells us atoms in their elemental form have oxidation number of 0. For example, if I give you this chemical reaction, you identify in this chemical reaction who is in the elemental form. Okay? So we know this is element, this is element. So these two are element. And then you can answer the question very quick. So for every Na atom, the oxidation number is 0. For every Cl atom, even though in Cl2 there are 2 Cl atoms, but for each one of them, it is 0. The second rule is oxidation number of monatomic ion is the same as its charge. So for this second reaction, we have this monatomic ion, these two are elements. So this is 0 from rule number 1, this is 0 from rule number 1. So every zinc atom is 0. Every Ag atom is 0. What about this Ag1 plus ion plus 1? What about this zinc 2 plus ion plus 2? So that's how we use the first two rules. And obviously this word has limit because we have a lot of those not element, not a monatomic ion. So what you do, you will go to the next rule. The next rule tells us the sum of oxidation numbers in a neutral compound is 0. The sum of oxidation numbers in a polyatomic ion equals the charge on the ion. Remember, you counting every atom when you sign the oxidation numbers. So usually, we will use a convention. We'll use the element symbol to representing the oxidation number for every one atom. For example, when we have NaCl, we'll begin to setting up the equation use Na for the oxidation number of sodium for each one sodium atom. We'll use Cl for each one Cl atom. So we have one Na plus one Cl equals 0. So this equation has two variables. We cannot have a unique answer. We have to use the next couple of rules. Rule number 4a, rule number 4b, or rule number 5. So whatever you come up with an answer, and then you just come back. If you have two variables, you find one answer from the next couple of rules. If you have three unknown, you find an answer for two of those unknown, then come back solving for the last one. So for this problem, there is two unknown. We don't know what is Na, what is the Cl. We find out what is Na, then we will stop in going further. We will come back to this rule. We plus this, we substitute this Na by the plus 1 to get this equation. Then we solving for Cl. So therefore, Cl becomes -1. So if you have those polyatomic ion, for example, nitrate, and you will set up the equation like this, so that equals -1. And where are those numbers come from? So those numbers come from, so this 3 come from this 3. This -1 come from this -1. So once we have this equation, so this equation again has two variables. Just using the next couple of rules. If you have two variables, finding an answer for one variable, then come back. So we find an answer for O in rule number 5. Then we back into this equation. We substitute -2 for O. We get this new equation. Then we solve for N. We're solving for the last one. All right, so what is the rule number 4A, 4B clearly? So 4A tell us if we have group 1A metals, what is group 1A, group 1 metals, which is Li, Na, K, rubidium, and cesium, you will give them a +1. So then the group 2, which means beryllium, magnesium, calcium, strontium, and the barium, you give them +2. So rule number 5 has this table, and this table has a priority. So the one on the top will take the higher priority. And
Can
so
you go back for 1 second?
Okay.
Sorry.
Okay, no problem. That's
all good.
Okay. So yeah, this table has the priority. So if you set out the equation using rule 3, so if you come to this table and you will see if you need the number for F, you find the number for F first. If you need the number for H, then you have to say if you need the number for F. So you know what this means. So again, we see this nitrate, and we said we set up this equation, and we don't know what is N, we don't know what is O, so you don't have an answer for both of them. So you go to rule 4. So rule 4 will tell you nothing about both of them. Then you come here to this table, rule 5. So you check one by one. We don't have fluorine, we don't have H, but we have O. Therefore, give the O -2 number from this table. Then you're solving for N. So that's how we get all the number by using these 5 rules. All right. So again, if you find out the number for the element and before reaction, after reaction, so if the oxidation number increases for the element is oxidized. If the oxidation number decreases for the element, then the element is reduced. Right. So though I have this chemical reaction equation, and those oxidation number is also kind of easy to find out. So for zinc solid is 0, for H plus is +1. For zinc 2 plus ion is +2. For H2 gas, and you have 2 hydrogen atom here. So each one hydrogen atom is 0. So if I give you those numbers and try to identify what element has been oxidized or what element has been reduced. So the definition is, if you have the number for the element before the reaction, after the reaction, so for zinc before the reaction is 0, after the reaction +2, so the number increases, therefore zinc has been oxidized. So similarly, you have the number for hydrogen element. So we have H before the reaction for every one H. This H element is +1. So after the reaction is 0. So then we can see the number decreases. So we can say the H hydrogen has been reduced. Okay, now what you want to see in this slide, there's more concept, which means what are the so-called agent, and in the homework we call them oxidant and reductant. Okay. So oxidizing agent or oxidant cause something else to be oxidized by taking electrons or electron away from them. A reducing agent like the zinc cause something else to be reduced by giving them electrons. And oxidizing agent being reduced themselves, reducing agent being oxidized themselves. So that's how we identify who is a reductant, who is oxidant. So from this, for this question, so zinc has been oxidized, therefore zinc solid is the reducing agent. And H plus has been reduced, so therefore H plus will be our oxidizing agent. Okay, so then do a similar for this question. And I give you this chemical reaction written as everything together, which means you have the half reaction for the reduction, half reaction for the oxidation, but this is all together. If you want to identify who is the reducing agent, who is the oxidizing agent, just sign the number and say who has been oxidized. So whoever has been oxidized will be the reducing agent. And we can see the number, let's say, for this monatomic ion, so this Br here is -1. So this is the compound. So we can think about 2 times H plus 2 times O equals 0. So you're solving those equation. I mean, you cannot solve the equation for both of them. You have to get a number first. So you go to rule number 5, you will see the H gets number first, that's +1. So if H is +1, 2 times +1 +2, so therefore O is -1. So even though most of the time oxygen is -2, but in this particular hydrogen peroxide, so oxygen is -1. So then this is easy because this is monatomic ion +1. This element is 0, so we have 2 Br, each Br is 0. And this is water again. So you can set out the equation 2 times H plus 1 times O equals 0. So you get +1 for H first, then you will have -2 for oxygen. So therefore, what happened to Br? So Br change, change from -1 to 0, so the number increases. So therefore, Br has been oxidized. And if Br has been oxidized, so that Br1 negative is the reducing agent. So Br1 negative AQ is our reducing agent. And let's see who has been reduced. Let's see, oxygen has been reduced. Why oxygen has been reduced? We check its number. So oxygen number changed from -1 to -2. So therefore, the number goes down, and so therefore the element has been reduced. So if the element has been reduced, so whoever have the element will be our oxidizing agent. So therefore, H2O2 is the oxidizing agent or oxidant. Okay, so next we want to study how to using the two half reaction to balance some of those chemical reactions. So the oxidation and reduction can be written separately and balanced separately. And each of them we will call them a half reaction. We will use them to balance overall redox reaction. Let's see, for example, SN2 plus and Fe3 plus react. So we can see who is oxidizing. Let's say we will write the oxidation reaction or the oxidation half reaction is zinc 2 plus becomes zinc 4 plus. So the number, the oxidation number increases. So therefore we know this is oxidation. Another way to know is oxidation is produce electrons. Oxidation reaction will produce or yield electrons. The reduction reaction, which means the oxidation number decreases. So we go from the Fe3 plus to 2 plus. So this is the reduction half reaction. So another way to know this reduction, so reduction reaction gain electrons, or the electron on the left side as the reactant. Oxidation reaction yield or produce electrons, so the electron on the right side as a product. Okay, so then this table gives us synopsis to balance equation using the two half reaction. So if I give you a redox reaction and you want to balance it, usually you decide in that given equation what is the half oxidation, what is the reduction, and then you also know like what kind of environment you have. Is it in a basic solution or in an acidic solution? So once you know the two half reaction, you write oxidation reaction, reduction reaction, then you balance them, follow a similar approach. So in each of these two half reactions, you balance the atom that is not O and H first. Once that is balanced, then you will go to the second step, balance the O and H. So you are usually first balance the O, but obviously you have to balance all the other atoms that are not O and H. So once you come to this step 2 or B, you want to balance O. You don't use oxygen atom, oxygen gas, you use H2O. So if you need 1 O, just use 1 H2O. If you need 3 O, then you use 3 H2O. So obviously, when you're adding H2O in your equation, you're also adding H. So therefore, you have to balance the H by using H plus, not H2, not H, but H plus. So if you are balance the equation in a basic solution, once you adding H plus, you balance all those atoms, Then what you do, you are adding hydroxide OH1 negative on both sides to neutralize all those 8 plus. And so we will not have too much questions for the basic solutions. I will just only to practice some of those questions in acidic solutions. So once you balance all the atoms, you balance the charge by adding electrons, because electrons always carry negative charge. So just adding electron either on the left side or right side to balance the charge on both the half reactions. Okay, so once you have both of the half reaction balance, balance the atoms, balance the charge, then what you do, you will multiply by a common factor to make the electrons in the 2 half reactions are the same. Then you will combine or add in the 2 half reactions, cancel out or combine same species. So we will use one example to go through the process. So this is the example of the oxidation reduction titration. So we have MnO4 negative has the purple color. And then we have the other reactant C2O4 negative, which is the colorless. You can see from the picture, once you adding this purple color MnO4 negative called permanganate into the solution, if there are still C2O4 negative in the solution, then the purple color of the MnO4 negative disappeared. But as the reaction goes on, as you adding more and more MnO4 negative, so finally you will use up or you will consume all the C2O4 negative. So therefore, the purple color of this MnO4 negative will stay in the solution. And you know you have the equivalent point. So the overall reaction between these 2 reactants, so this permanganate and this C2O4 negative, so this is the overall reaction. So right now, obviously, the equation is not balanced. So to balance this equation, you will use the procedure. You first sign the oxidation number, say what is your half for 2 half reactions. So from this, we can see here, this Mn will be plus 7. So each one O is -2. So -2 times 4 becomes -8. -8 plus 7 becomes -1. So then here we can see you will see the number for oxygen, -2. So -2 times 4, -8. And so therefore this carbon will be +3. So +3 times 2, +6. +6 with -8 gives us -2. So this is clear +2. And here you get oxygen -2 first, and +4 for carbon. So once you get the number, then you know what happened to the Mn. So Mn has been reduced because the number go from +7 to +2. Carbon has been oxidized because carbon's number changed from +3 to +4. So therefore, you are right. The oxidation reaction for the C2O4 negative. And to balance this equation, you will balance the atom that is not O and H first. So the atom not O, not H is carbon. So to balance the carbon, or right now the carbon not balanced because you have 2 carbon here on the reactant side, and you only have 1 carbon. So therefore, to balance the carbon, you are adding coefficient 2 in front of CO2. Okay. So then by doing that, you balance the carbon. Once you balance all the atoms that is not O, not H, then you begin to checking your O and H. So this problem just happened. Once we put 2 here, the oxygen also balanced because we have 4 oxygen on the left. We have 2 times 2 oxygen, 4 oxygen on the right. So oxygen also balanced. And that's only two elements. So carbon is balanced, oxygen is balanced. So what do you do next? Try to balance the charge, okay, by adding electrons. So we have -2 charge on the left. Right now we have 0 charge on the right. So therefore, you have to balance the charge. The only way to balance the charge is adding electrons. So therefore, you are plus electrons here. You plus 1 electron, you only have 1 negative. You plus 2 electrons, you add in 2 negative. Okay, now we finish balance this half reaction. So this half reaction, everything is balanced. So next, we write the reduction reaction equation. So in this equation, we have 2 elements. We have manganese, we have oxygen. So we first check the element, not oxygen, not hydrogen, which is manganese. Is that a balance? Yes, so that is balance. And so therefore, next, you are going to balance the oxygen. So what do we use to balance the oxygen? We don't use O2, we use water. So one water, we use H2O to balance oxygen, okay? So we need 4O on the right, so therefore we add in 4 H2O, okay? So then the problem is when you add in H2O to balance the oxygen, you also introduce or you add on the hydrogen, you add in the H. So therefore you have to balance the H. So you will use H plus to balance H. Okay, so we can see here we have 8H, have a 0H here. What you do, just adding 8H plus on the left. All right, so now all the atoms are balanced. Next, you balance the charge. So how many charge on the right? 0 charge here, +2 charge here, -1 charge here, 8 times +1, so +8 here. So +8 -1 give us +7. So you want to balance the +7 with the +2. What do you use? You use electron. So therefore, you need the electrons because electron has negative. So adding every 1 electron give you 1 negative. Right now I have 7 plus. You want to go to 2 plus. So therefore, adding 5 electrons. So now this equation is balanced. So after you balance all the equation, both the equations, both of the half equations, you try to put them together. Okay. So we copy the 2 balanced half equation as here. Before you add them together, you need to make sure they have the same number of electrons in them. So in this reaction, in this oxidation reaction, you have 2 electrons. In this one, you have 5 electrons. To make the 2 half reaction have the same number of electrons, usually you will find out the common numbers. So for this question, what you do? You will take this equation times 5, take this equation times 2. What that means, is you take this 5, multiply onto all the coefficients. You take this 5 times 2. Take this 5 times 2. And take this 5 times here. This means 1 here. So do the same for this. So take this 2 times 4. Take this 2 times 1. Then take this 2 times 1. And take this 2 times 8. And take this 2 times 5. So that what we mean by multiply the equation by some numbers. When you multiply equation by a number, you multiply all the coefficients by that number. So after you do that, both equations sure have the same number of electrons. And let's check that. Okay. So that's how we multiply 5 onto the first one. And we multiply 2 on the second one. No, they have the same number of electrons. So 10 electron, 10 electron. So this 5 comes from 1 times 5. This 10 comes from the 2 times 5. The 10 comes from 2 times 5. Okay, so 2 times 5 is 10. 2 times 8, 16. 2 times 1 is 2. 2 times 1 is 2. 2 times 4 is 8. So once we multiply both equations by the numbers, we get these two new equations. In these two new equations, one thing for sure is the number of electrons are the same. So therefore, when you adding them, one equation has the number of electrons on the right, the other equation has the number of electrons on the left, so they cancel out. That's actually the only something that has common in two equations. Everything else is unique. So therefore, we will just simply cross this out or drop this out, and then everything else remain. And so then that's it. But you need to make sure the equation is balanced by checking all the atoms. So we make a list. So we see our first element is H. On the left, we have 16H. How many H on the right? 8 times 2 also 16. Next element is manganese. So how many Mn on the left? 2. How many Mn on the right? 2. So that's balanced. Next, we check in the oxygen. Okay? Oxygen here 2 times 4 is 8. And here 5 times 4, 20. So therefore we have 28. So here we have 8 times 1 is 8. Then here 10 times 2 is 20. So therefore also 28. So oxygen is also balanced. Then next will be carbon. So how many carbon we have on the left? 5 times 2. So 10. How many carbon on the right? 10 times 1, also 10. So also make sure you check the charge. So what are the charge altogether on the left? So here you have 16 plus, and then you have 2 negative, 2 times negative. Then here you have 5 times negative 2, so 5 times negative 2. Okay, so 16 minus 2 minus 10 equals what? Plus 4. So let's check. We have plus 4 on the left. So how many charge on the right? So here 2 times 2 plus equals plus 4. There's 0, there's 0, so plus 4. Okay, so therefore we confirm this equation is balanced for everything, balanced for all atoms, and also balanced for the charge. So as I said, to balance the redox reaction in a basic solution, you follow the similar procedure, but just adding one step, adding this step, which means adding hydroxide to neutralize the H plus. Okay, so next section is we'll study those cells, which cells, which means using some of those chemical reactions, make a device to produce electricity or use electricity to make some of those non-spontaneous reaction happens. So for this first type of cells, we call them voltaic, named after some of those scientists. So in the voltaic cell, we will use the spontaneous reaction to produce electricity. You can see in this picture, we have two beakers. In one beaker, we have one metal is zinc. Then we have the solution zinc sulfate. In the other beaker, we have the blue solution. The blue solution is actually the copper 2 sulfate, the typical color of CO2 plus ion. Then we have the copper metal. So by the reduction or oxidation potential, so zinc relatively easier to be oxidized, and copper is more eager to be reduced. So oxidize means lost electron, reduce means gain electron. So therefore, there's a natural tendency for the electron flow from the zinc to the copper. So what this device do is try to harvest this natural tendency of electron flow by using the device. So make the electron flow not directly from the zinc metal to the copper metal, but goes through this wire. So therefore, we can use the electricity to light up a light bulb or to make some of those useful work. So in a spontaneous redox reaction, electrons are transferred and energy is released spontaneously. The energy can do work if the reaction flow through, or if the electron flow through an external device. And this is the voltaic cell or galvanic cell. So in the voltaic cell, you will typically have two electrodes, and you will have these two half reaction happens. And oxidation means lost electron. So the oxidation reaction will happens at the anode. So we'll give those electrodes. So usually the electrodes are some metal. The metal may be actively participating in the chemical reaction, or the metal is inert, not actively participate in the chemical reaction. So in this voltaic cell, we have two electrodes. So these are the electrode, and this electrode called anode, and this called cathode, and this a piece of metal here. You can use anything that's not actively involved in this reaction. In this half reaction, what really happens is the reduction of H plus. So you can use some of those inert metal like platinum, nickel, or graphite. So as long as some solid material that can conduct electricity but not participate in the chemical reaction can be used for those type of half reaction that do not have a solid. So for this half reaction, it has a solid zinc metal itself. So therefore, you don't have to use anything else. Just take the zinc metal as the electrode. Okay, so when you connecting these two beakers, so as soon as you connect it, so the electron will flow out from zinc atom. So zinc atom becomes zinc ion, and so therefore, if you don't balance the charge, so you are building up more and more plus here, so plus and plus and plus ions. Then here will be opposite. So you will take those H plus away. So initially in the solution, the positive ion, negative ion is balanced. So what do you do? If you take away those plus charge, so there here you have more and more negative. So therefore, you will use this sort of bridge. Use this sort of bridge to balance the building up charge on the anode, on the cathode. So if you building up more and more positive here, so sort of bridge has ions, so negative ion migrate to this anode to balance those charge that produced from the oxidation of zinc. And here, so obviously you will have more and more negative. So those positive ions from the sort of bridge come over to neutralize or to balance the charge that built up in this cathode. So the cations are formed in the anode. Then the cations are disappeared in the cathode. So therefore, you had to use a sort of bridge to balance those. Usually on the anode, because oxidation reaction happens, so the metal become oxidized. So the metal anode, usually they were lost mass, and so lost mass, and then give out the electrons, and then electron flow into the cathode. So then those cations will capture the electron on the cathode being reduced. Okay, so then this question is describing a voltaic cell. Okay, I think we'll stop here and we'll continue this chapter 20 next week. Okay, so everyone have a nice, good weekend, and I will be here at 10:30 for the office hours.
Dr. Wang,
Mm-hmm.
if we still have questions about the lab tomorrow,
Okay.
how would we contact you? Do we do it over Zoom or just email you?
Either way. If you want to ask, you can ask now, or if you want to ask in the office hours, or you can email me.
Oh, do you have office hours tomorrow?
Tomorrow I will have office hour from 3:30 to 4:30. So today will be from 10:30 to 11:30. What's
Okay.
question? You have a quick question?
Oh no, I just I was wondering just because I haven't finished my post lab, so I was just
Okay, yeah. Just you can either email me or tomorrow 3:30 to 4:30, or some other hours. You email me. You can. If I cannot explain in the email, we can set up another Zoom meeting.
Okay, thank you.
Have a good day,
Welcome.
Dr. Wang.
Okay, you too.
Have a good day, Dr. Wang. Thank you.
Okay, welcome.
Thank you, Dr. Wang. Have a good day.
Okay, you too, Naya. Bye.
Bye.
Dr. Wang.
Ariel?
Can you go back to a sample exercise 20.1?
Okay. 20.1. Yep, right here. Let me share the screen. Okay, do you see it?
Yes, I see it.
Okay.
So I didn't write down any of the work because I was printing out the notes as you were starting to do chapter 20.
Mhm.
And I got to here and I wrote down the first step, but I
Okay.
missed everything else.
Okay, so for this one, you want to identify the reducing agent and the oxidizing agent. So we know the reducing agent will be the one that has been oxidized. The oxidizing agent is the one, reactant that has something been reduced. So therefore, to answer this question, just first sign the numbers for all the atoms. I did not go to, we not have that slide. Let me just, this one, right?
Yes.
Now let me, okay. So therefore, you first sign the numbers by the rule, sign the, let's see, the so-called oxidation number, right? So the first one, the monatomic ion. So this is the monatomic ion. So -1 charge means -1 oxidation number.
Okay.
Okay. So next one is a compound. So you set up the equation. So you see you have 2H. So therefore 2 times H plus 2 times O equals 0. So you have two variables. You don't know what is H. You don't know what is O. So once you go to rule 5, you find out H equals +1. So therefore, say H is +1. So if H is +1, so you have 2 times H, so 2 times +1. Then plus 2 times O is 0. So you solve this equation for O, so O becomes -1. Right? Okay.
Right.
So then the H here is also clear. This H is the ion, monatomic ion. So Br here is the element. So this Br here is the element. And we know element has the number, oxidation number 0. So for this H in H2O is still +1. For the O in H2O is -2. Okay. So then we compare, let's see what happened to this element Br. So the element Br, the number go from -1 to 0. So the number increases. So Br has been oxidized. So bromine been oxidized. So then whoever been oxidized, or whoever have the element being oxidized, so therefore this Br1 negative aqueous is our reducing agent. Okay. So then we'll see what happened to H. H, nothing happened. So the H before the reaction is +1, +1, and +1, right? So then, yeah, what happened to oxygen? We can see oxygen, it happens, it goes from -1 to -2, right? So the oxidation number for oxygen decreases. Therefore, you can see oxygen being reduced. Okay, so then whoever have the element being reduced is our oxidizing agent. I mean, it's the reactant. So the reactant has oxidant in it is H2O2. Okay, so because H2O2 has oxygen, and this oxygen in this chemical reaction going from left to right being reduced. So therefore, H2O2 is our oxidizing agent. So that's how you kind of tedious step by step to find out what is the oxidizing agent, what is the reducing agent.
All right. Thank you.
You're welcome. Okay, any other questions? Okay, so I will end the meeting and I will come back in a few minutes for the office hours. Okay, so if I don't see you in the office hours, goodbye and have a good weekend.